Okay, so I wanted to follow up with you guys with what we talked about on Friday when we Google met. I know a couple of you weren't there. So we need to go over a velocity versus time graph again to give you some more, at least some more practice with this. So as you can see, we have velocity over here on the left side of the graph, which is at 7 meters per second. And then of course time, it looks like we end here at 23 seconds. So we have 3 different intervals here where the velocity is different. So from 0 to it looks like 3 seconds, the velocity is increasing. As you can see, it goes from 0 meters per second to 7 meters per second in only a 3-second time interval. So if we found the slope of this particular line right here, we know that we went up 7 meters per second and then over 3 seconds, which gives us 7/3 meters per second squared. Now, that is the acceleration. So hopefully you remember that we talked about this. It goes position, velocity, acceleration. So velocity is the derivative of position, and then acceleration is the derivative of velocity. So what's really important for you to understand is the slope of this graph, the slope of a velocity graph, is acceleration. Sometimes we call it dv dt, but that's also known as acceleration. So we have a positive acceleration because our velocity is increasing. So from, it looks like 3 seconds until we get to most likely 19 seconds right here, we have a constant velocity. If your velocity is constant, that implies that your acceleration is equal to 0 meters per second squared. So again, this could almost be like a real life thing. So if you were stopped at a stoplight at time 0, well, for say 3 seconds, you accelerate and then you reach the speed limit and then you continue to go the speed limit until a certain amount of time before you have to slow down again because there may be a stop sign, a stoplight, and in this case, that would happen at 19 seconds. So you accelerate quickly for the first 3 seconds, you accelerate none because you have a constant velocity, and then it looks like from 19 seconds until we get to 23 seconds, you are braking. So we go down, it looks like 7 meters per second, so that's a negative 7 meters per second in 4 seconds. So that would be negative 7/4 meters per second squared is our acceleration right here. Now you'll note, our velocity is actually positive this entire time. There is not a time the velocity is negative. There is only one time in which the acceleration is negative, and that corresponds to the velocity decreasing. So you need to understand this concept, which is, if velocity is positive and your acceleration is negative, that means that you are slowing down. So that's like you in your car again, and you see a stoplight, you're going to slow down, but you had a positive velocity. It's not like you go in reverse. You're slowing down in this interval right here. Now, let me write this down again. We have PVA. So we've gone from velocity down to acceleration. That's what all of the slopes represent, are these. They represent acceleration. So we need to go backwards from velocity to position, and we can actually determine how far we've traveled in this time interval. So if we go from here to here and we talk about this triangle right here, I'm shading in. If you take, that's a triangle, so we'd have the area is equal to 1/2 the base, which is 3 seconds long, times the height, which is 7 meters per second. So the total distance traveled in that time interval would be 21 divided by 2 meters. So basically 10.5 meters is how far we've traveled in the first 3 seconds. Well, then we have to find the area of this rectangle right here, which should be really easy. Our area would be equal to, we're going from 3 seconds to 19 seconds. So therefore that is 16 seconds, and we're going at a rate of 7 meters per second. So all we need to do is figure out what that total would be if we multiply those together. So that'd be 70 plus 42, So 112 meters is how far we travel. So 112 meters is how far we travel in the time interval from 3 to 19 seconds. Then we need to finally figure out what this is right here. This last triangle. So this last triangle has a height of, we do A equals 1/2, 7 again, times 4 seconds for its base. So the area of that triangle would be equal to 28 divided by 2, which is 14 meters for this part right here, 14 meters. Okay, so the total displacement and the total distance traveled in this particular time interval is going to be these numbers all added together. So we're talking about 112 plus 14, which is 126 meters, plus 10.5, so 136.5, I think, unless I forgot what I was doing. Meters is the total distance traveled. Now, let me get out, hit the wrong thing there. Let me get out of here. Okay, so the next thing that we need to talk about is how to write this. So the distance traveled for our time interval can actually be written from 0 to 23, the absolute value of the velocity graph. Now, this velocity graph is always positive. It's always above the x-axis. So it so happens the distance traveled is going to be exactly equal to the displacement because we have no negative velocity ever. So the displacement formula is actually this. Displacement would be the integral from 0 to 23 of v of t dt. So let me tell you again what this actually says. This is called an integral from 0 to 23. That's our time limit. Those are called limits of integration. So 0 is where we begin, 23 is where we end. All right, this is a velocity graph. That's why you put v of t. With respect to time, this means with respect to time. Okay, so the integral of that, we already figured it out. It was 136.5 meters. This one is also 136.5 meters because there was no negative velocity ever. So these are the formulas for distance and displacement. They're called integrals, which are the opposite of a derivative. So remember, you need to remember this. The derivative of position is velocity. That's the rate of change in position. The derivative of velocity is acceleration. That's the rate of change in velocity. The integral of acceleration is velocity, and the integral of velocity is displacement. So that's what we've done here. So hopefully you can see how this works. I'm probably going to give you one of these as practice on maybe a Google form later, but hopefully this gives you some idea, again, some more practice of how this works.